All right. Hello, everyone. It's me again. This is for statistics, problem set 4, the last one of this time, I believe, and the one before the test. Once again, disclaimer, I'm not always right, don't take it as such, but we're going to run through what I've got for this so far, and hopefully it'll be helpful. So, let's start off quite simply. Number 1. So we've got here, if you can sort of see on the right here, Number 1 here. In a computer store chain, all PC tablets are sold with the option to purchase a discount coupon. We can see that 47 out of the 229 people who bought upmarket tablets bought an option coupon. And we see the same thing for 25 out of 178 of the low-priced tablet buyers. Okay? We want to conclude, based on 90% confidence interval, that the people buying upmarket tablets are also more willing to purchase option coupons. First of all, let's set our variables, okay? We're going to find the pi hat. Remember, pi hat is the sample, okay? And I'm going to do U for upmarket and L for low priced, okay? We can see quite clearly here that you've got a 47 over 229 for the upmarket, and you've got a 25 over 178 for the low market, okay? Now, after doing this, we also need to set how many people are in each group. Again, this is fairly easy. We're just doing NU and NL, which is going to be 229 and 178. This is going to be very important later. Now, let's think about how we can sort of go through this hypothesis test, okay? Now, what is the question asking? Is it possible that people buying upmarket tablets are more willing to purchase option coupons? If that were true, that would mean that the proportion in upmarket is larger than the proportion in lower market. Okay, so that's going to be an alternative. But what's our null, right? So our null must be that, well, if our alternative is that it has to be larger than, then our null is that is that essentially that the upmarket is going to be either equal to or lower than the lower market. So that's our null. And we can also express the H1 now as pi u larger than, only larger than. Remember, you've got equal to or smaller than for the first one. Now it's just larger than. We can also represent this as the gap between them. Okay, you can also kind of work this out yourself, but you can say also that pi u minus pi l must be smaller than or equal to 0. Okay, that means they're quite similar. And you can also say that H1, that pi u minus pi l has to be larger than 0. Okay, sort of like that. Okay, well then, let's give this a try. Now, I'm going to specifically mention a formula here, and I just need to get it up, so bear with me here. As you can sort of see here on the top right, this formula for this question is actually contained within week 10. Now, this might be a bit annoying to some of you guys, given that we've currently only done week 9, haven't really gone on to week 10, but it is in here, after all. We can see that we've got a random sample with different number of observations for 2 different groups and different proportions. And we're testing with a significance level. Okay, here, this is a 2-sided test, essentially. You could also do, where is it? Yes, where is it? Oh no, wait, hold on. Yeah, that's it. Yeah, so you've got a 1-sided test here, which is actually what we're doing because we're merely testing for over. Okay, so you can see from our base hypothesis that we've got a less than or equal to. Okay, this means we're going to take what's in the bracket here. So our formula is that if the sample means of x and y, which we're just going to use u and l, so the sample means there are going to be larger than the positive z alpha over that hot mess. You can kind of see that where that is. So you got pi there over nu plus, oh dear, pi that 1 minus, then you got nl. If that's true, then we can reject it, okay? Now, inserting all those values, if you can sort of see that, hold on, can I make that bigger? I cannot. Hopefully you guys can see that. You can see quite clearly there that you've got for this value here. So for the sample proportions minusing each other, the gap is 0.00647 which is actually larger than on the right side, which is 0.0488652151. Also, this value in here, okay, you see that just regular pi hat? That's just going to be the number of people that got the offer coupon in general. So if we add up all the people who did the option coupons and the entire sample size, you get, what was it? Yeah, 72 over 407. Okay, so you will be able to get that. But yeah, given that it's larger, we've proved it true, and therefore there is sufficient evidence to reject. Therefore, people who buy out market tablets are going to be more likely to buy offer coupons. Okay? If you want more detailed notes, just look at my notes in the description. Okay, number 2. So, a newspaper article reported that 400 people in one state were surveyed, and 75% were opposed to a recent court decision. Ooh. The same article reported that a similar survey of 500 people indicated only 45%. Construct a 95% confidence interval. Okay, so there's a formula for this, as a matter of fact. This is within my formula sheet. I think it's in my formula sheet. I'll include my formula sheet in the description as well. But simply put, the formula is quite simple. Let's state the first one as x and the second one as y. So you have pi x minus pi y, which is the difference, is equal to the difference in the sample, so your sample proportion difference. Let me put those hats on. How lovely. And then the interval is defined by the area within the margin of error. So the margin of error here is, z alpha over 2. And then you've got the sample proportions here. Dueling it out, you know? Oh dear, come on now. Pi x hat. And then of course you're putting that underneath the you're putting underneath the number in there. So number x. Yeah, so what we're going to be doing here is we're going to try to find what the question gives us, and hopefully that'll lead us to our conclusion. So, in this case, we need first of all the sample proportion. Quite clearly, the sample proportion for x, as we can sort of read there, is 75%, so we'll just put 0.75. The sample proportion for y, though, is that it's 0.45, okay? Now you can kind of see the gap already here, it's like 0.3, yeah? So, we're also going to have to plus or add something here, and this whole thing here, so z alpha over 2. This is a 95% confidence interval. So alpha over 2 means that we'll be doing, that's 5% remaining, and then half it. So it's 0.025, yeah. So 0.025, you get, for that value there, let me just double check I'm getting this right, just give me one moment. Yep, you get 1.95996408 as your sort of front thing there. And you can sort of fill in the gaps from here. You've already got that population proportion, and we know that nx and ny are equal to 400 and 500 respectively. If you do all this correct, then at the end, you should have an interval between 0.239154243 and 0.63608457567. So between, essentially, 23.9% and 36.1%. So remember, this is the gap, okay? So there's about this big of a gap between both population proportions. Okay. Also, wait, I had a question from someone on the chat that I didn't quite answer. One moment. Let's see here. Someone said, is two-tailed? Yes, it is two-tailed. So this specific one would be two-tailed because it's merely asking for the interval. Okay, just this constructed interval based on the data. It's not asking you for a hypothesis here, actually, weirdly. It's not asking you to prove that this is true or this is not. It's asking for you to basically say, what's the interval? Yeah. So, number 3. A politician wants to estimate the proportion of constituents favouring a controversial piece of proposed legislation. Suppose a 99% confidence interval exists. So 99% confidence means that the alpha is going to be 0.01. And that it extends most... Oh yeah, this is determination. Okay, so the formula for determination is actually quite easy. Okay, so if you want to know... Go away, ruler. It's always clicking on you. So for sample size determination, you have n is equal to z squared alpha over 2 p 1 minus p over b squared. Now let me just go through all that. Z squared alpha over 2 is fairly self-explanatory. You guys know what that is. It's the value you get from the normal distribution. P here is the proportion. Yes, this is proportion. So yeah, is it proportion? Yeah, hold on, let me just double check here. Yeah, oh yeah, we don't know what P is. Excuse me. But B we do know. Okay, so far, let's first of all start off with that. We knew that it was a 99% confidence interval. So it was A was 0.1. So A over 2 is just 0.05. Oh wait, sorry, add an extra 0 in there. Which gives us, that is a pretty good confidence interval, which gives us finally the Z alpha over 2 as 2.57582936, and then we square it. So we're going to put that in there. All right. So let's just slide that up. That's going to be over there. So let me just make another equation entirely. So n is equal to that. P1 minus p we don't really know. So we're going to do P1 minus p over there. Because remember, we are also looking for the sort of, yeah. So we don't know the possible proportion. Okay, because we don't, remember, the politician wants to estimate the proposed proportion of constituents. We don't know that yet, so we can't insert that. But we do know that the margin of error, as this says here, it extends 0.05 on either side, right? So there we have that, which gives you essentially a thing here. So varying on the value of p, the value of p can change, right? But the thing is, p varies in an interesting way. So think of it as sort of like the number of people required is dependent on this number at the top, 2.576 squared over 0.05 squared, times this P1 minus P thing. So what is the maximum? Because remember, we're asking for how many sample observations are needed to be the max here. What's the max this can be? Okay, well, actually, if you think about it, it follows sort of a quadratic. You have P being 0 here, and you've got P being 1 here. Because both of those are going to cancel each other out, it gets a bit weird. But honestly, intuitively, you can say that, okay, when is this going to be biggest? Oh, it's when P equals 0.5. Okay, so that's when it's going to be biggest. So after you insert all those values in, okay, you end up getting n is equal to 663.4896892 people. Now, of course, we need to round up, because if we did 663 people, again, it would be too small, and if it's 664, it's just over, which works for us. So we're rounding it, and it's becoming 664 people. Now, I have heard that if you round that Z value over there, you can get a higher number, like 666 or something like that. Oh, how satanic, right? So be careful not to round too severely when it comes to the value of the Z alpha, because that's going to affect you quite a lot. Okay, we also want to go for number 4 now. Number 4 considers, first of all, we want to know if the concentration exceeds or doesn't exceed 3%. Okay, so in this case, we're kind of doing means here. So the null hypothesis is that concentration is at 3%, which we're going to put 0.03. and then the alternative is going to be that it's larger. Okay, so remember this is a one-tailed test. One-tailed, one-sided. I like tailed, you know? Tailed makes it sound kind of cool. So, the formula for this, for especially means, is that you should reject it if the sample mean is smaller than the mean for the mean for the null minus z alpha, and that is the known variance over the sample size. Okay, so currently we know that okay, so from production run, impurity concentrations follow a normal distribution. So we know that impurities follow a normal distribution with sample size, yeah. Okay, well that'll be for later. But we know that the standard deviation here is 0.004? Yeah, 0.004. So because that's 0.4%. A random sample of 64 peels from production runs taken, so we know that n is equal to 64, and the mean impurity concentration, which is the sample mean, is found to be 0.0307. There we go. So, now we can test. So we're going to insert our values. We've got 0.0307 is smaller than 0.3 minus Z alpha, which in this case, because it's, what is the confidence interval? Oh, there we go. Oh, yeah. Test at the 5% level. So that would be a 95% confidence interval, which would give you, yeah, there it is. So you've got the negative value there. So you've got Z alpha is negative 1.644853667. Yeah, I think that's right. Is it right? I swear that's right. One moment, let me just double check that. Okay, seems my method here was a bit off, but no matter, let's go back to it. So getting the Z alpha here, we can see that it's negative 1.644, or it could just be 1.64. It doesn't really matter. It's either way. I'm going to do the positive, actually. We also know that if we could reject the null if this is true, that if the normalized value is smaller than the alpha value. No, it's larger. Isn't it larger? I think it's larger. Is it larger? It is larger, yes. So it's larger than. Okay, so let's input our stuff. We've got 0.0307 minus 0.03 over the 0.004 divided by root 64, which is just 8. Okay, calculating this, it's probably going to be quite small. Actually, it might be quite big. Who knows? So we've got that divided by 0.004 divided by 8. What do you know? It is 1.4. Okay, so given that 1.4 is not bigger than 1.644, okay, we can reject this. Okay, so we accept the null hypothesis essentially here. Oh, let me get back to my problem set. Yeah, let me just check that we got the same thing. No, we did not. Never mind. Wait, what happened? Well then, there we are. Just ignore me for now, I've got to redo that. But that is the answer. You can reject the null. No, you can't reject the null. No, you accept the null. One moment, I've really got to double check this. Where did it go? There it is. Nope, now I am sure. Yeah, it's, you keep the null. Okay, so it's close enough to be fine. So we're good. Hooray! There is not. Well, let me underline that. This is not true. There is not sufficient evidence to contradict. Okay, there we go. So, we're done with that. So now let's do the p-value for number 4. Now you find the p-value for finding the chance that the sample mean is going to be larger than the population mean. So we're doing it for probability of x, where we're defining our normal distribution in terms of x. X is larger than 3.07. I've changed it back to regular percentage just to make it easier. Where x is distributed normally with mean of 3, and you got 0.4 there as your variance. Now what this would give you, if you were to plug this into a calculator, is that the probability of x is larger than 3.07 is around 0.43053981168. And that is your p-value. Okay, it's going to be a roughly 43% chance that it's going to be larger than. Okay, what a shock, right? But given that, it's actually quite possible, you know? Okay, if the x value is larger, like imagine, if you would, a normal distribution like this, okay? And you've got, that is a terrible normal distribution. Something like that. That's a little better. If you've got 3 right here, okay, 3, and you've got 3.07 right here, okay, and remember, your deviation here is bloody 0.4, which is this big, right? 0.4 on each side, okay? Given that this is already 50%, right? Doing the one for 3.07 is going to be very similar, okay? In fact, I'm shocked it's even that, you know, high already. I had that low already. I think it should be a little higher. But honestly, this is how it is, okay? So, now we're left with number 5, which is the most annoying. First of all, let's just find the sample mean and the sample variance. So the sample mean calculated from this should be either 8.82, or if you want to do things in terms of percentages, you can do 0.0882. Either one of those. Calculating sample variance. Remember, sample variance is different to population variance. Okay, so calculating sample variance, you use the n-1, which should give you. Let me just double check this here. Where's my thing? It's down here somewhere. Here it is. So you can have either a 2.401 ... sort of thing, or you could do 0.0240129464052. I can't speak. I used this because it's slightly more accurate, but you guys do what you want. Yeah. So plugging this in. So the thing is with this, you know the sample mean and variance, but you are estimating for a mean here. Okay, so we know we're estimating for a mean. That's a crucial thing. So we look at the notes for a mean. Okay, and so we want to test the claim at the level. Okay, so what's the claim? They're saying that it's 10%, right? We want to know if that's true. So this is a two-tailed test. We're testing if it's true. So our null hypothesis is that their population mean is 10 or 0.1, whatever works for you. Okay, and our alternative here is that it is not 10 or 0.1. Okay, so that's essentially what we're testing for. Okay, to find that, we need to find the acceptable interval where it'll allow it. Okay, given we know the population given that we know the population mean as 10%, we can use that, but we don't know the variance of the population, so we can't use that. So we're going to use the student's t-distribution this time. So we're stating here the interval is going to be calculated with mu 0, which is the null hypothesis mean, plus or minus the t-distribution of the degrees of freedom -1 Oh, and we also know that n is 10 here because there's 10 people. And then you've got the alpha over 2. And then you've got the standard deviation sample over n. And that's going to be how you calculate it. Obviously, we're going to put 0.1 in that place. To calculate the t-value, you're going to need to look this up, probably on a t-calculator site. I will include a link to that also in the description. Got to make the list here of what I'm going to include in the description. The number is fairly obvious and the s is fairly obvious, so you can kind of go ahead. This gives us an interval of 0.1 plus or minus 0.017176642959554, which gives an interval of the 0.0828233 or whatever. And then you've got 0.117176 ... So this gives you an interval based on the sample between 8.282% and 11.718%. Okay, so that's what we so far got. Given that our observed value, which was this, is at 0.0882, it's actually within it. It's within the acceptable region. So we don't have... Wait, hold on. What is happening? Oh, yeah. Oh, I messed that up, right. Okay, one moment. Sorry, I'm so goddamn tired. Nope, I was right. I keep second guessing myself. That's sort of my thing, I think. It's weird. It's very weird. So you can see here that it's included within it. Okay, so this is one method. Okay? One method of doing this. There's another method where you've got... One moment here. The econ chat is typing. Guys, could you just... I am trying to work. Let's see. Yeah, so you've got the decision rule based on values of t instead. So we can also establish the t as the same as before. So you've got sample mean minus the real mean, but you're using the sample variation instead of the one that you usually have. And what we say here is that it'll... Yeah, so if our t-value it exists outside, so there's an interval, and that interval is going to be the negative and positive values of t n minus 1 and then a over 2, yeah. So that out of those negative values. So it's going to be between these two. Let me just double check this. Yep, that's correct. So if it's outside this interval, we can reject it. Okay, so that's the thing. Now, what the t-value is here is that it is, what was it? Yeah, it was 0.0882 minus the 0.1. Yep, over the 0.02401, you get the idea, over root of 10, which gives you actually negative 1.553946772. Okay, so that's your test statistic. Now, your actual value of t, though, is a different thing. The value of t, I believe you get here. Let's go to the formula sheet, actually. And let me just go back to my my good old t-distribution calculator. So for a t-distribution, yeah, here it is. So for the t-distribution calculator, you can see that I'm adjusting the site. For degrees of freedom, we input 9. For the probability, we put 0.025. Was it 0.025? I think it was. What was the confidence level? At 5% level. So because it's at the 5% level, we're going to put in it's 0.05, and because we're dividing by 2, it's 0.25. And then we get the t-score, which is negative 2.262. As this is actually within it, okay, because you've got 2.262 and negative 2.262, As this number here lies within, we can't reject it. So we accept the null for 5, okay? You're accepting the null hypothesis. So what we're saying here is that, yeah, sure, we can say that you can claim that there's a yield of 10%. Now, what's the p-value for this one? Well, you use your test statistic you just used, and we want to figure out what's the chance that we get something smaller or larger than that test statistic. Okay, so we're going to do that. The probability that t is less than 1.553. Now, given that this is two-tailed, you're going to actually have to multiply this value by 2 afterwards. You eventually get, and I believe I'm correct in saying this, if you put in the t-score we just got, which is negative 553946,772, you get, oh wait, hold on, I forgot to put the point in there. Oh, there. Yeah, I know that, shut up. Yeah, here we go. You get 0.07. 773. And given that it's two-tailed, we're going to times it by 2, which gives us 0.1546. This here is our p-value. Okay, I think we're done. Hopefully that's helpful. Yeah, bit of a wild ride, that one. I know it included stuff from week 10. That might make some people mad. Honestly, it's not particularly great, but it is what it is. Okay, hopefully that should be good. I should be making a video on the homework for this week tonight. Again, I will include my homework, the calculator, and the formula sheets in the description. Okay, see ya. Bye.